here I talk about basic. Okay, so I will present one specific model. First, the binary independence retrieval model from Robertson and Stark-Jones, which is one of the first probabilistic models, which was also then evaluated. There are older probabilistic models, especially one by Maren Kuhns from the 60s, but couldn't be evaluated due to certain limitations. And so here, in this case, the basic idea is to represent queries and documents as set of terms. Like I said before, the probabilistic models originally they were restricted to sets of terms only, and so they didn't use the rich representation or the richer representation of bags of words that they used in the vector space models at that time. So we have the query representation is a set of terms actually, and then the document representation is also a set of terms. And I see these probabilities for some reason are written the wrong way, so it should be the probability of relevance given D divided by the probability of non-relevance given D. So I'll have to correct that. So that's a linear function of the probability of relevance, or the so-called odds. So if you are doing online betting, you might have odds. So the odds of a document being relevant, that's the probability of general probability of relevance. So what's the proportion, overall proportion of relevant documents in the collection divided by the probability of non-relevance, so that's 1 minus the probability of relevance. And then for each document, you have two products, one running over all the terms that are common to the document and the query, and the second one running over the query terms that do not occur in the document. Then you have two parameters, PI and SI. So PI is the probability that the TI occurs in the random relevant document. So the probability that this specific term occurs in a relevant document, and TI on the application relevant bar, that's the probability that the term occurs in the random non-relevant document. And so here you take here for the terms occurring, you take the ratio between relevance and non-relevance for occurrence, and then of course for non-occurrence it's 1 minus the PI, probability that it does not occur in relevant and probability that it does not occur in non-relevant documents. So therefore the terms not query terms not occurring in the document. That's how this probability of relevance is computed. And as I said, there's still an error. I will have to correct that. And so to look at an example of this model, so assume we have here 20 documents, and for one query, some of them are relevant, so R means the document is relevant, some are non-relevant. And then we have two query terms, T1 and T2. And so the first group of documents, they contain both query terms. Here, these contain only the first term, these contain only the second term. Then we have 3 more documents containing none of these terms. And now, since they have the same representation with respect to the query, we can already also compute the probability of relevance for these documents. So here, 4 out of 5 documents are relevant. So in terms of the ranking principle, they all have the same representation, and so their probability of relevance is 0.8. Then here we have 4 out of 6, so their probability of relevance is 0.67, and here it's 0.5 and 0.33. But that's independent from the BIR model. Let's just be regarding this representation. Now we will see how the BIR model does. For that, we have to compute the probability for each term that it occurs in a relevant document. So overall, we have here 4 plus 4 plus 3 plus 1, so 12 relevant documents. And T1 occurs here in 8 of them. So the probability that the first term occurs in a relevant document is 8 out of 12, so 2 over 3. And then for the first term occurring in a non-relevant document, we have altogether 8 non-relevant documents, 1, 2, 3, another 3, another 2. So 8 non-relevant documents, and the first term occurs here. And no, here, first term here, here, and here. So 3 times in non-relevant documents. So it's 3 over 8. Similar with the second term, it occurs 7 times, so 4 plus 3 times in a relevant document out of the 12. And with respect to non-relevant, so that's 1. And here another 3, that would be 4 out of 8, so it's 1/2. And furthermore, we have the general probability of relevance, 12 out of 20 documents are relevant, so it's 3 over 5 the document is relevant. And now with these parameters, we can apply the formula from the previous slide after we have corrected it. And then we get these values here. We get 0.76 for the first group of documents, 0.69 for the second, 0.48 for this group, and 0.4 for the fourth group. And now you see that the values computed by the BIR are different from the probability of relevance that we just get by counting. Why? Why are these values different? Here.
Portion of the relevant and non-relevant features of these clusters. And within these terms. Within the 2 terms.
Yeah, yeah, of course, it's different, but that's not the real reason why the estimates. Why is the model not correct? Any model is an approximation of reality. But yeah, the model makes certain assumptions, namely about the independence, stochastic independence of distribution. So I didn't mention this explicitly, but so these products that we have here, they are based on the assumption that the 2 terms are independently distributed, both in relevant and non-relevant documents. And that's not completely correct. That's just an approximation to reality. And that's the reason why the values computed by this model are not the exact values that we should get. But that's the problem with any model. It's just it's only an approximation of reality, and but that was also, so coming back to the article by Cooper that I showed initially, he showed that the actual assumption was not that it was really so naive justification was really this independent distribution of the both terms. He showed that it's more a linked dependence, that the dependence between the two terms is the same in relevant and non-relevant documents. But that's very sophisticated topic, but yeah, it took EIR people 15 years to figure this out, why the model was working so good. Okay, but coming back here, so it's only approximation, but the important point is the ranking that we get here is the same. So the optimum ranking with respect to the probability of relevance would be first this group, then this group, and this group, and this group. And with BIR model, although our probability estimates are different, we get the same ranking. And that's the important thing that we get the ranking that's close to the optimum one. And so this also explains the good performance of this model. Okay. What's the obvious limitation of this model? Within document frequency. Yes, that's the point. Yeah, it just looks at the presence or absence of a term and doesn't consider within document frequency. And so this led to BM25, what Robertson developed 20 years or so after the initial model. And so he did a heuristic extension of the BIR model. 10 years later, Chamiamati came up with a theoretic explanation for what Robertson did. But initially it was heuristic extension, and this also explains 25, because it was his 25th attempt of a heuristic extension. Okay, so the idea was now how can we consider within document frequency? And so let's assume here we have our term frequency, and here we have the term weight. So before we had just binary weighting, we just have with 0, we are here, and then if it's 1, then we are here. So we just have a stepwise function. And so now we want to consider something that increases monotonically within document frequency. And the question is now, what's the best form of function? So should I do a linear weight proportional to the frequency? Should I do a convex function that initially increases strongly and later the curve is flattened, or a concave curve which initially grows very slowly and then very big? What do you suggest? Which of these three functions? So the red one. Why?
I think that the first occurrence is the most important, and then if there are 32 or 36, the difference is somehow small.
Yeah. Other opinions?
It's the same thing, but the idea is the impact should diminish the frequency.
Yeah, also authors, they repeat many words. So remember, a lazy students or for seminar talk, you ask them for written manuscript in addition, and you want 10 pages, but initially they only have 6. You have to say, yeah, but it should be minimum 10. So what they do is, well, they just rephrase things and repeat certain words and so on, blow it up in order to come up with 10 pages. So they certainly will repeat themselves. And yeah, Gianni Amati, he actually did a systematic study of these effects, and as a byproduct, theoretic explanation of justification that PM25 is an approximation of a more theoretic model. Okay, so that's the basic idea. We go with the red curve, and the underlying heuristics, they mainly build on what was originally developed for the vector space model of Salton's group. And so it's a set of heuristics. So the idea is that the weight of a term should be higher. The less frequent the term occurs in the collection, that's the inverse document frequency IDF, and that's also implicitly in the original EIR model. But then the M25 looks at with the document frequency, so the more often the term occurs in the document TF, and also, of course, document length should be considered. Remember the example of the lazy student blowing up his document. So then, of course, document length should be considered some way. And so they came up with this formula, but we don't know to know the formula by heart, just to get the general idea. So as parameters, you're considering now the document length and in relation to the average document length in your corpus. And then you have the occurrence frequency of the term in the document. And then you have 2 more tuning parameters. So be the weight of the length normalization. Our port is length normalization, and the weight of the occurrence frequency. We first have a length normalization parameter capital B. That's the sum of 1 minus P plus B times the ratio between the actual document, the length of the current document versus the average length. So if the current document is twice as long as the average document, that would be factor 2. But then you weight this by B. How strong is the influence of this length normalization? If it would be 0, you just ignore document length. And if it would be 1, then you would say the length normalization in this example is just 2, factor of 2. But of course, you can then, with lowercase b, you can control it. And then you normalize within document frequency parameter b. And so then you use this normalized within document frequency. And here the weight of the occurrence frequency comes into play, the parameter k. So you have the normalized with the document frequency divided by k plus LTF. That's your with the document frequency weight, and that's then here the full formula, and then in principle you plug this into the logarithmic version of the VIR formula that I showed you before. It's a prefix for each term weight. That's the basic. Okay, so that's basically the BM25, so the most popular retrieval function, which is nowadays used many applications as baseline. Of course, you always have to be careful with the choice of the parameter b and k. So when you are describing an experiment using this baseline, you always should specify the parameters b and k. Because otherwise, reviewers might assume that you cheat and you use parameters b and k that gives very poor performance for b and 25, so that your own method can shine even more. But of course, we shouldn't do that. So better be transparent and say which parameters you choose, and then you can also try to find the best. If you are using new collection, so you first should do some kind of grid search or so to find the best parameter values for p and k. Okay, that's about the classical models. And the next step is the parameter-based models. The next step is learning to rank. And here's a figure redrawn from publication from 1992, where I described the general idea of learning to rank. Well, at that case, at that time, I described it as description-oriented learning, but basically it's the idea of learning to rank. So when you look here, that's what the BIR model does in principle, is you have a specific query and now you get relevance information from some documents. So the basic idea to apply the BIR model is the system presents some documents to the user, and the user judges their relevance. And from these judgments, the user, the system derives the parameters pi and si. For example, the system could present the 20 documents. Of course, that would be way too much. But the basic idea is some documents to the user. And then the system estimates the parameters of the model. And then these parameters can be used to rank the remaining documents in the collection. That's the basic idea. Learning here, training here, application here for further documents for the same query. But of course, the limitation is for the next query, you have to start all over again. First, train on some documents, learn the parameters, then apply them. Then historically, there also was this Maron and Kuhn's model. They proposed the idea of document-related learning, that the document should be observed with respect to some queries, and then based on this experiment, one could on this feedback, one could weight the terms to which the document is relevant, give them higher weight, and then this information can be used for further queries. Web search engines do something similar. They observe how often a document is clicked upon and use this as a kind of document related learning these days. But it's still document specific. When you have a new document, you have to start all over again. And the feature related learning now is different. So here you are regarding features of queries, documents, and terms. Not the specific objects, not the specific query or the specific document, or also here the terms occurring in these queries or so, but rather the features of queries, documents, and terms, and you learn on a training sample with certain features, documents, and queries, and this knowledge then can be applied to other documents, to other queries, and to other terms as well. That's the basic idea of learning to rank. So instead of focusing on specific queries, documents, and terms, you are looking at features of these objects, and then you can apply this knowledge onto other queries, documents, and terms. And so, a bit more formally, so instead of before we estimate the probability of relevance given query and document, and now we abstract from specific queries and documents, so we define a feature vector x of q and d, and then we use a training sample to learn a function g of x as an approximation of the probability of relevance. So the probability that the query document pair represented by this feature vector is relevant. So before in the BIR model, for example, we compute the probability that a document containing these terms, for example, is relevant, but now instead we are looking just at a feature vector. And then so we derive this function g, and then we apply this function to new queries and new documents. We can apply it without further training for this documents. That's the basic idea. So that means that the ranking problem has been transformed into a classification problem for the estimating the probability that this pair represented by this feature vector belongs to the relevant class. We have two classes, relevant, non-relevant. Then we have the classification problem. Probability belongs to the class. So that means in that case we can use arbitrary classification methods, and the biggest win is that we have a free choice of representation of queries and documents. We are now able to deal with more complex representation, so we can go beyond simple tags of words for representing documents. And that's what we have, for example, now in web searches. That all web search engines do. They consider information about the document, like for example, page rank, or how often the document has been clicked on in the past. Then we have query and document features. So use ESSIR2022, the term location, does the term occur in the title or body of the document. You can consider word distance and so on. And you can also consider other metadata like features of the URL, and anchor text meaning other documents referring to this document. What's the text that belongs to this link in the other document? That's the anchor text. And in principle, you can also consider information about the user or even the social network. So that's all my feature, that are elements of my feature vector. And then for training, for example, you can use click-through data, and then you can estimate the probability that the user will click on this document and rank documents according to the click-through data. Or, as I said, also use other training data if you have low-paid workers for you that manually judge relevant. You can train on this data and get better estimates. So that's the basic idea of learning to rank. Okay, now there are different flavors actually. So you in 2009 wrote a very nice long survey article or book, booklet. And so first, simple approach is pointwise. That's more or less the approach I described before. where you just map queries, pairs of queries and documents onto the interval 0, 1. So in that case, our training data consists of query document pairs with relevant judgments. So you can also use an ordinal scale instead of binary scale. You can use the ordinal scale. And then the learning task is regarded as a classification, or can be also regarded as numerical or ordinal prediction. So for example, you have an ordinal scale and simply do numeric prediction. There are also specific methods for ordinal prediction. So that's the oldest approach. Then the next idea was to do pairwise ranking. That well, the user is not really interested in the probability of relevance. Okay, that might be the case in some areas, for example, classification or routing of documents, so you need a precise cutoff and so. But when you just regard the task learning to rank, then it's the important problem, the order of the documents. That's what the user is most interested in. So this leads to the idea of pairwise learning to rank. In that case, you are regarding triples of queries and 2 documents where you have reference relation. So which of the 2 documents is a better answer to the query? That's the idea. And again, that's a classification problem. Should D1 come before D2 or D2 before D1? That's what you want to predict. But the important thing is that here you focus just on the ranking part. Still, the limitation is that here in this approach, the question whether you have one document in first and second rank in the right order versus the one in rank 9 and 10, they are of equal importance to this function. But empirical studies show that most users just look at the first few documents that do not really go to 9 and 10 or whatever you consider, how many ranks you consider. So the third approach is list-wise, where you try to apply a retrieval metric that you try to optimize ranking with respect to a specific retrieval metric. So in that case, your training data consists of queries with lists of documents specifying an ideal rank order. You tell the system these documents should be ranked in this order. And then the algorithm aims at optimizing the ranking with respect to a specific evaluation metric. So hear more about metrics this afternoon from Nicola. Most of the more sophisticated metrics, they actually consider the ranking, like for example, this geo rank by position. So that's the third approach that focuses, tries to be a better approximation on the real application. Okay, so much as brief introduction into learning to rank. Of course, nowadays you have neural networks and they are a complete game changer because now you can use, consider many more features. So some years ago, so 10 years ago, there was a web page of Google where they explained, so without neural networks, or before neural networks, that they initially were starting with about 3,000 features that they defined originally. And then they did the feature selection, came down to 200 or 300. And these 200 features then went into the actual classification method that they used. prediction and classification of the, for example, support vector machine or so. But nowadays, with the neural networks, you don't need this feature selection. You just throw in everything you have, and if you have enough training data, you get an even better result. Yeah, that's how it works. Okay, and then also here with these traditional methods, you have to think about feature transformations. So I mentioned that use PM25 weights and so on, all of that. And nowadays, neural networks, since they are able to do also these nonlinear transformations and so on, don't need to bother about feature transformations. That's all in the network. Okay, so much about learning to rank. Questions? Now, last part of my talk, I want to address interactive retrieval. So far we just have assumed that the user has specific information need, and we want to find best possible ranking for that. Well, the classical view on interactive retrieval is as follows. Well, we have user has information need, formulates a query, sends it to the system, gets results, and evaluates the results, and then, yeah, either it was satisfying and we are done, or not, then the user has to reformulate the query in order to get a better answer. That's the basic idea. So the basic idea is to optimize the query. The user has to optimize the query, then the system is able to give the best possible answer to the right query. There have been empirical studies showing that this is not true, meaning that information search consists of a sequence of connected but different searches. It's not just about optimizing the one query, it's more that the task remains the same and you formulate different searches, and each search result may trigger new searches. So only the task context remains the same. And so this means that this model is not really helpful. So the main goal of the search is accumulated learning and collection of new information while searching. That's what empirical studies showed. The task remains the same, and it leads to a sequence of searches addressing different aspects of the problem, and yeah, maybe also the understanding of the problem changes during the search. And so one approach for dealing with this was Bates' berry picking model. Based on the assumption that there's a continuous change of the information need and also of the queries during the search. And the information need thus cannot be satisfied by a single result set. We should not aim for the one query that returns the optimum results. Instead, we just have to support formulating different queries. And the idea is that we have a sequence of selections and collections of pieces of information during search. Like if you go out in the forest and pick berries, then you are hopping from bush to bush and pick some berries and fill them in your basket. The same way you are searching for information. So yeah. You start here with Q0, returns a document, but this gives you an idea for another query. Then you looking through documents, you find another term that you might include. You find another document. Then you formulate Q2. You find another term, formulate Q3, and so on. So you are adding swapping terms in your query, changing terms, and finding some documents, and the documents, they are what you have in your basket at the end of the berry picking. That's the basic idea. Well, is this model considered in any way by today's web search engines? Model is from 1990, though it's not fairly recent. Fun?
They think that we might search for something. That's why they comment these. So I think it was
but for example, in web search, there's no real support for collecting things. The other thing is also whenever I have a hard problem and I try different query formulations, after I have tried 3 or 4 variations, I don't remember which variations have I tried already. There are commercial search engines that have a feature for looking at the query history from the 1960s and 70s, but current systems don't have it.
Yeah, I would say the problem here is that it's so tight integrated into web browsers. So I guess search engines assume that you use your browser and maybe open new tabs and do it like that, but it's not directly supported by the search engines. For example, if I just press very simply on the first result on Google, it will open the same tab. So it will replace my search engine with the website and it's gone.
Yeah.
And I have to take care of like connecting myself.
Yeah. Yeah, one thing, yeah, of course, is the collecting, but also the other thing is, yeah, you can always say you put the result in a new tab. That would be one way to get around, but the other problem is keep track of the query formulations. And unfortunately, there's no support at all. So as I said, traditional search engines from the 60s and 70s, they had that already, that you have the list of queries. So question is, maybe no one does these lengthy searches on the web. What do you think? Is there any need for supporting such kind of search process, web searches? Yeah.
for example, if we are analyzing search logs, we'll get this information of queries where the documents were clicked on. For the user behavior analysis, it's been very important.
Yes, yes, of course. Yeah, but the question is, what do you think? Are users performing lengthy searches with web search engines? Yeah, are they performing lengthy searches? Does this describe the use, at least for a certain fraction of users, does this describe the process that we
if users are working on a complex
yeah.
they can't do like this because it's
Yeah.
not like one used to do one.
Yeah.
I was just thinking maybe for some specific scenarios.
Yeah.
The user searching what's wrong with my phone and then they figure out, okay, something's wrong. How to repair it? Okay. Like 100 first repair.
Yeah. Yeah, now one might say, yeah, these are the last 1, 2, or 3% of users, and we have to serve the remaining 97% better. But some years ago, Jamie Tiran presented statistics from the Bing search engine. They found out that half of the queries come from search sessions that last half an hour or even longer. So 50% of the queries belong to this type of search sessions. And there's zero support for this type of search process. So there's room for improvement. That's all I'm saying. Okay, so what can we do? So, yeah. Let's go back to the probability ranking principle. Here, as briefly mentioned, the relevance of a document is independent of the relevance of other documents. That's one problem that's not really fits the reality. Second is the information need is assumed to be static throughout the search. Also not true. And furthermore, it deals with the user's judgment of ranking documents only, though it's not really, it only covers a small part of the interactive retrieval, meaning that other tasks in interactive IR, they are ignored. And so this led me to the interactive probability ranking principle. Here the idea was that we want to consider the complete interaction process, not only the ranking of the documents. Then that, of course, the different activities, they require different efforts or costs. So we have different costs for the different activities. Reading a document is, the snippet of a document takes longer than deciding whether a term should be excluded from the search. And furthermore, that we allow for changes of the information need. During the search, the information might change. And now the basic idea now of the interactive PRP is that we regard interactive retrieval as a sequential decision making. So for example, when you do a web search here, first you type in some words, and then the search engine might suggest you already some alternatives or extensions of your query. So you first have to decide if you pick one of these alternative formulations or go with the one you started. That's the first step. So you decide, no, I go here with my original query. Then you get a ranked list of documents. You look through these documents sequentially, and at some point might say, no, somehow that's not what I'm really looking for. Well, for that, the system suggests you now also searches related searches. You can think about now involving one of these related searches, or alternatively formulate something differently. So it's a sequential process to go through. And so that's a theoretic model some years ago. There was a work by Life as a Party, and we did that together with the Bing people. That's the B. They analyzed the interaction of Bing users. So here you have not only the normal result list, you have all types of entries here. And then you have here on the right side additional information from the knowledge graph and so on. And then they analyzed how users look at the different entries, and they found a pattern. For example, for this page, the typical pattern would look like this. And it's still a sequential process. So users have a clear idea in which order they look at which element on the screen. And if users don't have a clear idea, then that's bad interface design. When you do eye tracking experiments, which we also did when we came up, for example, in the medical domain with the new search engine, we did eye tracking experiment, we found all the flaws in the interface design. And of course, these nowadays, the web search engines, they are result pages that's highly optimized trained on many sessions. Once heard that Google, for example, they will do running experiments where certain elements were shifted pixel by pixel. Now, after each shift of one pixel, they were running another series of experiments in order to find out how well users appreciated this layout. So, assuming a good interface design, then the users have a sequential processing of the elements on the screen, and for each element, of course, they have to make a decision whether they now click on this element or go on. So the assumption of the linear decision process, that's the basic idea. At least it's a good approximation when you do, for example, even for a ranked list, when you do eye tracking or so, then you observe that users are not strictly following the linear order, but it's the best approximation that we have. So the basic idea of the interactive probability ranking principle now is to focus on a functional level of the interaction. So we assume that the usability problems have been solved. That's what we have the HDI people for. And so we have a good interface design. Now our system presents a list of possible actions to the user, and users evaluate the possible actions in linear order. So this linear processing, and furthermore, only the positive decisions or executed actions are of benefit for the user. So all the negative decisions we can ignore, they don't change anything, only the positive ones, they are important. And so the abstraction that we are using here is that we have situations with lists of actions. So here we are in situation as 0, and then we have choice 01, 02, 03, and so on. And user here clicks on the third choice, and then we get into a new situation. Could be also, for example, the change of information need or whatever. So in principle, we assume that we are in a completely new situation once the user has clicked item and has learned something. And here again, user goes sequentially through the list, clicks on an item, gets to another situation, and again. Okay, so here every accepted choice brings the user into a new situation. That's the basic idea. Yes.
So let's say the user clicked in the third position and they learned something. And then you include this information that the user has learned into the new search session. And then you exclude from the search.
In the next step, I take this as positive feedback, and ideally I would include this information to present a better ranking.
Okay, but let's say if I'm in a learning process where I'm searching to learn something, then once I have learned that, I don't want more of the same thing. I want something new that I want to explore more. Like does it include diversity?
Yeah, of course. In principle, you can also include diversity. And actually, there was a student in Glasgow who used the IPRP for diversity ranking. And he also had the quantum-oriented approach as an alternative. We found out that, in fact, the IPRP is at least one reasonably good solution to the problem. So just have to adapt it. So how you do the ranking in the next step, have to adapt that to the problem. That's possible. So here we have it again. Text, user moves from situation to situation. User is presented a list of possible actions. Then user decides about each of these actions sequentially, and then the first positive situation moves the user to a new situation. So now we will just focus on a single situation, and the question, how do we rank the possible choices that we present to the user. We have knowledge about what happened before, incorporate all that, and in order to present an optimum order of the possible actions in this situation. So for each action, we estimate the probability that the user will execute this action. Then we have a certain effort, so we are computing benefit. So negative value of effort for evaluating the possible action, and we have a positive benefit from a positive decision. So the idea is for each action we have a possible benefit, J, and then the expected benefit of an action can be computed as first we have the effort anyway, as soon as we look at this choice, and then with probability, the probability that the user chooses this action, the user will experience the corresponding benefit. That's the basic idea. So let's look at an example for the expected benefit. So, for example, the user submits a query, formulates a query, then may choose among the following actions with the parameter equals effort, probability, and benefit. So a user might add an expansion term to the query that costs 1 second, and with probability 0.3, that's what she wants, and the benefit would be 8. For example, a gain of 8 seconds for reaching the goal. Or the user looks at the first result list entry that takes 2 seconds, and with probability 0.4, that's what the user wants, and would give a gain of 10 seconds. Or the user goes immediately to the first document, and reading it might take 10 seconds. The user might pick the choice with 0.4, and the benefit would be 25. Or you could also present an aggregated summary of the top ranking that would take 5 seconds to look at. User will want that with probability 0.3, the gain is 20. Now you wonder in which order should these actions be presented to the user. And we see the first has a benefit of 1.4, the second of 2, third is 0 gain, and the last one has a gain of 1. So I would say 2. Here is the best one. User should look at the first result list in this example. So the basic idea is that you compute these parameters for all possible choices, and based on that determine the optimum ranking. Well, actually, the optimum ranking is not according to this value. You have to go to the paper which explains why this is not the optimum ranking. It's pretty close, but the actual ranking score is completely different. Just to give you the idea that it's these 3 parameters that you have to consider in order to determine a good order. In principle, you have the choice how to design your result page, and you have to really think about what's the best order in which to present the different possible choices. And that's one theory on how to do that. Well, actually, to implement that, there's a number of research problems. So first, there is the problem of parameter estimation. So you have 3 parameters. You have the selection probability, and in principle, this is the focus of many IR models. So whenever you are thinking about I could suggest some terms to the user. Also, you need scoring functions for these terms. And, but in principle, that's a probability that the user will actually want to have this term included. So that's what you try to estimate. And also you need to decide about the cutoff in some way. So that's one area of research. Then the effort parameter, well, you need more research. You need to observe users. So we worked on eye tracking, and I'll come to that in a minute, and have logs with timing information. Also use base for extracting this from the logs. And finally, the benefit, well, that's still somewhat open issue. And so what we have been focusing on is the saved effort. So you see below the following, I will explain that. So how close do I get to my goal? For example, to my goal of finding a relevant document. Assume that, yeah, in principle, we have search paths. So that's the situation the user is currently in. And there are 3 choices. And each of these 3 choices will lead to another set of choices. And then here with the star, we see the relevant document. So the task of the user is to make the choices that lead him or her to a relevant document. That's in this simplistic example. But of course, the search paths, they differ in the effort for reaching a specific goal, for finding the next relevant document. And so the problem is, how can we model the expected effort or benefit of the whole paths? What's the overall effort the user has to undertake to reach one of these relevant items? And one approach for doing this is with Markov models. So here the basic idea is that we have different states. A user is in different states. For example, here the user might formulate a query, that's one state, and then with probability 1.0 goes to the search result page, so that describes the web page, and then probability 0.9 looks at the first snippet, and from the snippet a user might go on to the next snippet, or click on it and then go to the document, or go back to the result page, or formulate a new query. And from the document also the user might go on to the next snippet, back to the result page, so the next page, or formulating the next field. So we have different states and with transition probabilities. That can be described nicely by Markov models. So how can we apply such a model to start? So here is a screenshot from an experiment we did. We had a modified book search engine. Users were given book search tasks. Here they formulated their query. Then we have the result list. And when they clicked on an item, they could see more info about the book. And then they could mark the book as being relevant, and it was collected in this basket, or alternatively, they could already decide about relevance based on the snippet only. And then what we did was we defined areas of interest for eye tracking. So we said, did a lab experiment with eye tracking where we defined areas of interest in order to identify for each moment where is the user currently looking at. Looking here at the query field, or here at which result item is the user currently looking at. Especially if the user starts scrolling or so, we have to be able to follow that how the where at which position which result this item is currently presented. Then here we have the document, here basket with the documents, and then you get an AOI sequence like that. So here each row is one area of interest, one rectangular area on the screen. Then, and here we have the time as the x-axis, and the gray gray bar means at that time this item is actually visible. This object is visible. So here the query window is always visible, but here we have the result list items. They are only visible at certain times. And yeah, that's realistic eye tracking data. Of course, you need some more heuristics, for example, for user to read something. I think the minimum time span is something between 50 and 80 milliseconds or so. They have to ignore all the shorter cases and things like that. And we also combined it with the logs. And here, yeah, we have it in a bit more detail, just the beginning of the search with the, so here we see in the beginning, just 4 result list elements were visible. And if you look here at the colored parts of these gray bars, then yeah, roughly speaking, the user is looking in sequential order, but there's also some backtracking, and so you need some good heuristics to get valuable information from that. And then we see that here the user was scrolling to the next items of the result list. Okay, so we combined the eye tracking data with logging data, so the user was actually clicking or submitting another query. And based on that, we were able to derive this Markov model. So here we have 4 states, the query, then the result list with the different result items, then the details, and then the basket. And the size of these circuits denotes the time. So users need 4.9 seconds for formulating query in this experiment. The single result item takes the user 2.3 seconds. Looking at the details, on average takes 15 seconds, and the basket 1.7 seconds. And then we have the transition probabilities. Also, the probabilities correspond to the width of the arrow. So after a query with 100% of the cases, the user goes to the result item. Then 85% the user just goes on to the next result item. So that's what we got from the eye tracking data. In 11%, the user then clicks on the result item and goes to document details. And in 24%, the user finds this document relevant. Other 75 not relevant or so. And then the user went back to the next result item, or in some cases formulated a new query. So having this data from the combination of eye tracking and logging, we can derive for any point in time when the user was where. So we can determine the selection probability, so the transition probabilities we have, and that's the selection probability of the IPRP. Then we have the effort, that's the time spent for an action. Well, these are just times that we have here. And the benefit, that's the saved time. So let's assume that we get want to get to the basket as fast as possible, how quick you get there. And well, in that case, with that model, with Markov models, that's a simple linear equation system. So we have the effort in the states that we have on the previous slides, TQ, time for the query, for the result item and the document. Then we have the transition probability from state X to state Y, transition probabilities. And then we can compute the expected times for reaching the basket state. We want to reach the state where we found a relevant document. Then TQ. So from the very beginning, we first have to formulate a query. Then with a certain probability, which happens to be 1, we go to the result item. And then we have TR. And TR, or the result item, we first have to look at the result item, lowercase tr. Then with a certain probability, go back to the query, and then we have TQ again. Okay, we are getting further away from our goal. But this happens, or we go on to the next result, this item, then we have TR again, or we go to the document, then we have TD. And TD is just the time for looking at the document, plus the probability we go back to the query, then we have TQ again, or we go back to the result item, then we have TR again. And so that's a linear equation system. All the numbers here, they are given on the previous slide, and we solve it, and we get TQ is 122.7 seconds. For TR, it's 117.8, and TD, that's 104.9 seconds. So we are looking at the document. That's how much closer we get to our goal, find a relevant document. So that's the basic idea how we can estimate the parameters, and based on that, estimate the benefit. That is how much closer do we get. Okay. So that was a lab experiment, and then we did a bigger experiment where we looked at an online search engine, and we took a log from the search engine with 90,000 search sessions. We only regarded sessions with at least 300 seconds so that we can learn something, and that left us with almost 2,000 sessions left. And now to show you the problem, when you go into practical problems, so before we had this 120 seconds or so that users take. Now here, what we found, so we looked at the time from the first snippet to the next, until the next relevant item was found. Because when the user has found a relevant item, then the user normally wants more relevant items and does not immediately formulate a new query, instead goes on to the next snippet. So that's why we regarded the time from snippet to the next relevant. So it might be the first snippet might be the first one after the query, or the first one after a relevant document. Time from this snippet to until the user found the next relevant document. And here we have the frequency distribution. So we see this ranges from about 10 seconds or so up to 1200 seconds. That's very nasty real world data. Normally when you do lab experiments, you have well-defined search tasks, and so you choose a certain amount of time. There's some variance, but more or less same. But this is real world. Users come with all kinds of such tasks. Sometimes they find the answer very quickly, and sometimes they really need a long time. So that's the problem we were dealing with. And so what we did was we had built an ensemble of Markov models. So instead of one Markov model, we used 5 different models, each of them specializing on certain areas of this time range. And then for a specific user, we estimated the probability that the user is in a certain time range and can assign the corresponding weight to the corresponding Markov model. That was the idea. So still an ensemble of Markov models. And that's what we got here. Then we, so the idea was now we wanted to do numeric predictions. So similar when you are, if you have a navigation system on your car with navigation system, how long will it take until you reach your goal? And here in this case, the system tries to estimate the time until you will find the next relevant document. That's what we try to estimate. And so we observe the user for some time. It's called cut-off time here. That's the time, how long we observe the specific user in order to get an idea how the user behaves. Is it a slow reader or a fast one? Does she click very often on items, or does she read through many items before she clicks, and so on? And then we had different, and then we make a prediction for the remainder of the sessions. How long will it take the user to find the next relevant item? Then we applied numeric prediction models, so support vector ranking, then the model M5P model tree, and K nearest neighbor. And in addition, we had a global Markov model, so the ensemble of the 5 models, and we see, well, they all perform very similar. So, of course, the longer we are able to observe the user, the better our estimates get. So the error reduces. But then we also develop personalized Markov models, where we integrate information about the specific user into our Markov model. Instead of using the 5 predefined Markov models, we adjusted the model parameters according to what we saw from this specific user. And the numeric prediction methods, they do this implicitly, but we had to do this explicitly for our Markov model. And it turned out we could do much better than all the other models with our personalized Markov models. So we are able to describe very well quantitatively how users are behaving. And okay, so this, yeah, it's just very preliminary work, so to say. It has to be refined. So far, we are not really dealing with document ranks. We are not distinguishing ranks.
Yes. Sorry, I was curious about your work. So, what are the assumptions of each one of the models? But what I understood, these models, they try to divide the previous slides. So the session lengths according to their characteristics, right? So that there are different assumptions, behavioral assumptions.
Yeah, the assumption is, yeah, really that you have information about a training set of users, of other users, plus observation data from the specific user. And now you want to predict how, for each specific user, how long will it take this specific user to find the next relevant documents or the remainder of the session. So for each relevant document that the user finds in the remainder of the session, you compute the time it took from snippet to this relevant item. In case there are multiple images. That's our that's what we try to predict, how long will it take this user to find the next relevant item.
So it's a combination of these 5 models.
No. That's it's a competition between these models. Yeah, we tried traditional models and then our own approach based on the ensemble of market.
And the support effect the question. And the just make a model they were using of course different from the from the things you use in market model.
Yeah, they use the same features. Yeah. That's why more or less why they behave similar. Yes. Yeah, we have no information about the task. We're just observing the behavior. Yeah, in order to improve, of course, it would be nice to have information about the task and content of the database and all that, but that's still missing so far. It's just purely behavior oriented. Just looking at the mark of the different stages the users go through. So, for example, for the result list items, since we didn't have eye tracking, we just had a lot. We did just a heuristic approximation. If the user submits a query and then clicks on the 5th item, then we assume that before the user has looked at the other 4 before. And then we just divide the time from query to the click, distributed over the 5 items the user has looked at.
Was it possible? I understand that it was not the purpose of the work, but is it possible to predict the length of the session based on the first few queries?
No, that's still an open problem. Certainly, that would be interesting. Yeah, we might do that in the future. Because we have a proposal look at that as well. Yeah, that's. I don't know if there's much work. Why do users finish a session? There might be very different reasons why users stop. Such topic on itself. Yes.
So the cutoff temperature is done based from the query to find the next row.
No. Cutoff means how long we observe the user until we start making predictions. That's because we need some observation. Because otherwise, for each user, we would, at the point 0, we would make the same prediction about every user because we don't know anything about the user. If you have users coming back to your system, if you know a user from the past, then this would be helpful in making estimates, but here we didn't have this information. So every user is new, so we had to observe the user for some time. So we could make any reason.
So how to define the session? Let's say if the first variant search for something, and then the second one I changed the topic. Like, is it considered that they changed like the topic?
Yeah, in principle, yeah, of course, if they change the topic, then we possibly consider that still as the same session. So that was lead us into.
So it was just like the time.
We only looked at the time. Many ways for improving. Definitely. But at least it shows, that's a way we could follow further. Because the goal, of course, is to guide users in the end. So far, we are just observing users. It's not of much value to tell user, well, you are a slow searcher. Okay, thank you for that.
I don't know if it makes sense, but let's say if I want to increase the user engagement in my platform.
Yeah.
So instead of giving them the right results, I want them to continue the search.
Yeah.
Can we use this model then to do the opposite? And maximize the time that they will stay searching for stuff.
Well, this is just a description. We just have the log data, but of course you can do everything. So in another study, it's not described here, we work with hidden Markov models, where we assume that there are different search stages. So that's our search phases. That users might go from, there are models that assume, for example, typically three search phases or so. In this experiment, we took the same data and only distinguished two search phases. And we were able to show that with this model, we can do better predictions. And so the idea would be that if you notice that with high probability the user has entered the new search phase, you might slightly change the interface for better support in the new search phase, for example. Possible. So, yeah, as I said, that's what we did with hidden Markov models. Then, we have to consider document ranks. So we models just assume that all ranks are equal, but of course that's not true. And we also did a minor experiment, small experiment, where we really found out that the further down user goes, the lower the probability. And for that specific task, we even could find out that after rank 9, it's better for the user to formulate a new query instead of going on through the search list. Query reformulation, that's also a thing we have not addressed. So usually one would assume that, with the reformulation, you formulate a better query for success. So these are all refinements that haven't been investigated yet. Okay, so that's just one approach for dealing with interactive retrieval. I just briefly mention other aspects of interactive retrieval. So context is a very important issue. So if you know about the location and time of the user and ask for a pizzeria, then you can make appropriate suggestions which pizzerias are nearby and also are open, or when you go to Amazon, when the online shop knows your complete online browsing history, can include that. So that's context. Then nowadays, these days, there's much work on conversational search, where in principle you also have different queries, but implicitly refer to previous one. What's a physician's assistant? What are the educational requirements to become one? So you have a co-reference, or here, so that's a co-reference, or you have something like a topic shift, or what's the difference between RN and PA? So you need context to decipher what PA in P refers to. So that's another important area of research, and last week at CIGA we saw several papers on that topic. But in principle, it's an enhancement of interactive retrieval. So models that we currently have to be extended. Well, to conclude, IR is about uncertainty and vagueness in user-oriented information systems. And current trends is that we move towards more knowledgeable objects. that we deal with interaction and conversation, and that we consider more complex, so in terms of personalization, and also with respect to the situation or work task, so especially the aspects I discussed together with relevance. Okay, that's it. So the remaining slides will just show the references that I used in this part. So further questions? So I will be hanging around today and tomorrow. Unfortunately, on Wednesday I have to leave. If you have any further questions, also I'm happy to answer them.
Thank you very much for great lectures this morning. So I'm still very curious about the user modeling. So this user models seem that get out of fashion, like was saying here, but a lot of things changed in the meantime. What do you think we should do now in terms of user modeling to platforms, let's say?
Yeah, of course. I think you have to extend them towards these aspects of the model that we have. We just have to consider these additional factors. So I think that's doable. Someone has to do integrate.
We need data to feed these models, and data that is not always public.
Yeah, of course, that's always the problem where you get the data. I admit that. Yeah.
But user modeling for search is very interesting. You mentioned the session.
Yeah.
But when you go to conversational scenarios, like you went in your slide,
yeah,
that may be even harder to get data to build those models.
Yeah.
So
that's why I'm not doing conversation search.
So it would be feasible to build synthetic user simulators. I know it's a bit of a chicken and egg.
Yeah, we are currently thinking about looking at simulators just for the standard interactive search, so without conversation. But in principle, try to extend that also to conversational search. Why not? Certainly worth trying. And of course, then still we will need some empirical data to actually train these models and test that. Okay, thank you everybody.